Hi, everyone. In order to multiply matrices, we first have to talk about multiplying vectors. In particular, a row vector times a column vector. So let's say we have a row vector like this with n entries, and a column vector like this with n entries. You have to have the same number of entries. Well, this may sound familiar. When you multiply the row vector by the column vector in this order, don't switch these. It goes this times this, plus this times this, plus this times this, plus this times this, plus this times this. And you can think of the result as either a scalar or a one-by-one matrix. It depends on the context. But does that sound familiar? This times this, plus this times this, plus this times this, da da da. It should remind you of a dot product. So when you take a column vector, a row vector times a column vector, then here you get 1 times 4 plus 0 times 5 plus 3 times -1. Again, remember for dot products, if you're like me and you tend to miswrite things, you might want to write down the products without writing all this, whatever works for you. 4 plus 0 plus minus 3, we get 1. Either 1 or the one-by-one matrix containing 1. Again, it depends on the context. Basically, it's the idea that the dot product yields a scalar, basically. Oh, and incidentally, it turns out that if we had a column vector times a row vector, we get something very different. It turns out that we get, well, we'll see. It's the multiplication table. It's the multiplication table. We'll see. All right. So now we can multiply matrices. And you might think, well, why not do what we did with matrix addition and just add corresponding, well, just as with matrix addition, just as we added corresponding entries, why don't we multiply corresponding entries for matrix multiplication? Well, MATLAB does have an operation for that, component-wise multiplication, but matrix multiplication is different. And it actually corresponds basically to linear transformations in linear algebra, Math 254. So first of all, when can we multiply matrices? Well, just like with matrix addition, it really depends on sizes, but in a different way. So our first question is, when can we multiply two matrices, and what would the size of the resulting matrix be? And then if the matrix product is defined, how do we get that matrix product, entry by entry? So the first issue here, given two matrices A and B, the matrix product AB is defined if and only if the rows of A and the columns of B have the same length. This makes sure that the dot products work out. That means that when these have the same length, it actually means that the number of columns of A, the matrix on the left, is equal to the number of rows of B, the matrix on the right. I'm doing this because it turns out I'm going to multiply matrices using a trick. Now, if this is confusing, I don't blame you because there's actually a better way of doing it. I should have mentioned that. You don't have to freak out too much about this. Let's talk about some tricks here. Consider the matrix product A times B in this order, where A is this 2 by 3 matrix over here, B is this 3 by 2 matrix over here. So again, we're going to ask, is AB defined? Is this matrix product defined? And if so, what is its size? So let's consider the sizes of A and B. We just observed A has 2 rows and 3 columns, so A is 2 by 3. B has 3 rows and 2 columns, therefore B is 3 by 2. The matrix product is defined because these two middle entries are equal. That corresponds to the notion that the number of columns of A is equal to the number of rows of B, meaning that when you consider a row, basically the length of the row equals the length of the column. So you can do dot products. But again, the number of columns of A equals the number of rows of B. But just observe and ask yourself, are these two numbers here in the middle equal to each other? If so, the matrix product is defined. And given that this matrix product is defined and AB is defined, what is the size of AB? What is the size of that matrix product? Well, take a guess. Take a guess. It's going to be 2 by 2. It's determined by the outer numbers. So if the inner numbers are equal, the size of the resulting matrix product is given by the outer numbers in that order. So AB is 2 by 2. In general, because you might be wondering, well, what if it's not square? If A is m by n and B is n by p, then well, first of all, the matrix product AB is defined because n equals n. These two middle numbers are equal. Given that this matrix product is defined, it turns out AB will be m times p. You might go, well, that's cute, but why is that? Well, when I show you the trick for multiplying matrices, we'll see why this is. Why it's the number of rows of A by the number of columns of B. We'll see why that is. Okay, now, if a matrix product is defined, how can you find the entries in that matrix product? You don't do it by just multiplying corresponding entries like we did for adding and addition. It's different. We take dot products. So, and remember, you don't have to remember this. I'm going to show you a shortcut, but here's the long way, the harder way. If AB, the book way, if AB is defined, then the entry in its ith row and jth column is the ith row of A times the jth column of B. Do you think you can really remember that? Me neither. I don't think I can remember that. So there's a shortcut. This is true, but there's a shortcut, which works a lot easier for me. Okay, so we're going to go back to the two matrices. Oh, wait, do I have? Oh, yeah, we have the two matrices here. Okay, we established that AB is defined. The result will be a 2 by 2 matrix. But what are the entries? All right. A traffic intersection model, streets. So here's the idea. We want the matrix product AB in that order because BA is a different deal. The matrix product AB. The matrix A on the left, I'll put here. The matrix B, I'll raise up here. And then lightly draw these horizontal lines through the rows of A. Not too thickly though, because you don't want to cover up the negative signs. I know this seems kind of strange, but you have to worry about stuff like that. And draw columns, draw these vertical lines through the columns of B. But again, draw them thinly, not too thickly, because you don't want to cover up ones and things like that. Strange considerations. Now here's the idea. Here we have the matrix AB. And right off the bat, you can kind of see why it makes sense that AB will be 2 by 2. Because here's the deal. We're going to take the dot product at each of these positions. I'm going to call this matrix product AB C as a single letter. So then this is C sub 1, 1, and so forth. Now for C sub 1, 1, the upper left entry, the top left entry, we take the dot product of the first row of A and the first column of B. The bottom line is you're going to take the dot product of the vector, the row vector, and the column vector whose corresponding lines intersect here. So for this entry, you take the dot product of this row vector and this column vector. That's easier to remember than it's the first row of A times the first column of B. So we do that. Now, it makes sense that, first of all, AB is defined because notice that the row length of A equals the column length of B. That ensures that we can take dot products. And the row length here is the number of columns. The column length here is the number of rows. So the number of columns here equals the number of rows there, which means that the matrix product is defined. But again, instead of worrying about that, okay, we had that earlier trick, right? Those two middle numbers were equal. Okay, right? That was the bottom line. The two middle numbers are equal, right? Two middle numbers are equal. And the result is 2 by 2. The number of rows of A times the number of columns of B. Look at this. Well, the 2 rows of A will give us 2 rows in here. The 2 columns in B will give us 2 columns in here. And it'll be a 2 by 2 matrix. So here you can see it better. An M by N matrix times an N by P matrix will give us an M by P matrix. Number of rows here by number of columns there. All right, so then we actually take the dot products. And I'll go through the rhythm with you. Let's go through the rhythm. Okay, so for C sub 1, 1, all right, the upper left entry, okay, the dot product is going to be, let's see, green. It's going to be the first row times first column here is going to be this times this, plus this times this, plus this times this. Okay. Again, if you're like me and you tend to miswrite things, you might just want to work the products in your head and write them down. Some of you might want to write all this, but it's going to be, think products, 4 plus the -3 plus the 0. If either of these is a 0, the result is 0 for that product. But it's 4 minus 3 plus 0, which is 1. So a 1 goes in the upper left entry. And then I'll show you the rhythms. The rhythms. Okay. For the upper right entry, it's going to be the first row of A times the second column of B is going to be this times this, plus this times this, plus this times this. Yeah. All right. So it's going to be, all right, the -1 plus 0 plus 0. -1. Right. -1 over here. C sub 2, 1. Row 2 of A times column 1 of B. Don't worry about that. Just work the streets here. Work on the streets here. All right. So for this entry here, 2 times 4 plus 1 times 3 plus 3 times 1. All right. So we have 8 plus 3 plus 3. 14. All right. And then bottom right entry, second row here times second column here. It's going to be 2 times the -1. Whoops, over here. 1 times 0, 3 times 2. What are the products? -2 plus 0 plus 6, which gives us 4. All right. So you put these in their correct slots. Oh, and by the way, I would not expect you to necessarily do it like this. In fact, I would accept answer only, although I think it would help you to do some work just for accuracy's sake. But the answer turns out to be this. I would accept answer only, but the thing is, you want chances for partial credit. And of course, our arithmetic can often fail us when it comes to speed, right? But bottom line, here's the matrix product. 1, -1, 14, 4. Do make sure that you're putting the correct numbers in the correct positions. Okay, so be careful about that. It's wrong if you put them in the wrong positions. Okay. Now, warning, matrix multiplication is not commutative. You could consider A times B and B times A, and they may not be equal. In fact, it's possible that one might be defined and the other is not. So AB and BA could look very different, or one could be undefined even, or both. And again, why is matrix, and think about it, when are they both defined? I'll have you think about that. Why was matrix multiplication defined this way? Well, it's related to compositions of linear transformations, which you'll see in linear algebra. Next up, identity matrices. And these are very important in linear algebra. Basically, what kind of a matrix acts like one? Next time.